Okay, so the special proof that we're going to do is we want to use the squeeze theorem to figure out what sine theta over theta is, because we want to know what the answer to that is so that we don't have to do it every single time. So if we can figure out what that answer is, then we can just use that as a shortcut in the future. So if you think about doing direct substitution, what is sine of 0? Think about the unit circle. 0's over here. 1, 0. Sine of 0 is 0, so that's a 0 on the top. And if I do direct substitution on the bottom, what do I get? 0. So I get 0 over 0, and what do we know about 0 over 0? It's an indeterminate form. We don't know how to handle it. And as of right now, later on we're going to learn how to handle 0 over 0, but right now we don't know. So right now this is a squeeze theorem problem, and so we want to learn how to handle this specific situation. Okay, does that make sense? Okay, so that's the purpose of this. So you're going to have your other notes, the squeeze theorem, that's going to work for some of the more complicated problems. This is going to work for some of the easier problems that fit something that looks like this. And I'll show you some examples of, like, once we learn this little shortcut, I'll show you how to do problems that are similarly set up, how we could manipulate them to use this little shortcut, okay? All right, so the first thing we're going to do is we're going to draw some triangles, or we're going to draw some areas that we actually know the area of, okay? So the first one that we're going to draw is this triangle right here. We're going to draw from here, right here. And then we're going to make the triangle from here. It's going to go from here to here. That's where the straight edge is going to be, from here right to here. Okay? And you're just going to shade that in. Do not shade too dark because we're going to write on top of that in a moment. And you can actually see we're making an inequality with the areas that we're drawing. Okay, so here's the next area that I'm going to draw. It's going to be from here to here. And this time I'm going to shade in the entire sector. So I'm not even drawing a triangle this time, I'm shading a sector. If you guys remember, a sector is a portion of the circle. Okay, and then for this one, I'm going to start right here, and I'm going to go up, I'm going to make a right angle. Then I'm going to take this, I'm going to extend past so it kind of meets that right there. So here's my right angle, I'm making a right triangle. And then there's my triangle right there, I'm going to shade that in. So we're going to compare the areas of all of these triangles. And you can kind of see how this inequality is working. So this is a triangle, it's got the smallest area. This is a triangle, it's got the largest area. Here's a sector, it's got the medium area. We cool with that so far? Okay. So the formula for the areas of each of these are going to be 1/2 base times height. Does anyone remember how you find the area of a sector? Yeah, it's the area of the whole circle, but only a portion of it. Anyone remember the formula for area of a circle? Pi r squared. Pi r squared, okay. And then we have to say just take a portion of that circle. So if we can figure out what this angle is, this theta right here, we would say theta out of a whole circle is how many pi? 2 pi. So theta out of 2 pi times the area of the whole circle. That's how you find the area of a sector. Okay. So to find the area of this triangle, that's what we got there. Area of this triangle, that's what we got there. Okay. So I'm going to take another color so I can write on top of this and we can still see what we're talking about here. I'm just going to go ahead and mark this. Here's my theta. Here's my theta. Here's my theta. Are we still comfortable there? Okay. So I'm going to say this right here, this is x comma y. We're picturing like the unit circle, right? That's like your x coordinate and your y coordinate. Would you guys agree with that? Okay. Just x comma y. Yeah, your x coordinate, your y coordinate is that point right there. So here's what we've got. We have, what's the radius of the unit circle? That's the degrees. Unit. Unit. What's the radius of the units? It's 1. Okay. 1. So from, that was a test and you passed it just barely. So from 1 to the edge, or sorry, from the center to the edge is a length of 1. So from here to here is a length of 1. From here over to here is a length of 1, right? So the base of this circle and the base of this triangle is a length of 1. Would we agree with that? The hypotenuse of that triangle is a length of 1 as well. Okay. Now we have the y coordinate of this point. We have x corresponds to cos, right? We're thinking of the unit circle. What does the y correspond to? Sine, okay. And you guys can see that the y coordinate is also corresponding to the height of that triangle. Would you guys agree with that? Okay. So the height of this triangle is going to be sine theta. Okay. Now, since we are drawing this, we're doing this proof in the first quadrant, everything is going to be positive. Are we okay with that? We're doing this proof in the first quadrant, positive everything, so we just don't have to deal with negatives. Okay. All right, so I'm going to go ahead and take this geometric picture and I'm going to convert it into algebra. So I've got 1/2 times a base of 1 times the height of sine theta. Are we good? 1/2 base times height. Okay, less than or equal to. All right, for the next one. Over here, what is the radius of this drawing? Same thing, unit circle. What's the radius? 1. Okay, over here, I got my radius of 1. I still have my angle measure, it's the same, it's my theta. So now I can do some simplifying. I can say that pi and pi cancel out. So I have theta over 2 times my radius squared. Good so far? Okay. All right, over here, somebody tell me what's the radius? What's the base? Base is 1, what's the radius? 1, so that's the hypotenuse. So radius, well, not quite the hypotenuse, but that little piece of it right there. Okay, so over here we have, I'm going to just label these. I'm going to take a different color. I'm just going to do black. Okay, so if that's theta, then this is the opposite side. Hold on. There we go. This is the opposite side. Everyone agree with that? Okay. This is the adjacent side. Do we agree with that? Okay. So we know that tan theta equals opposite over adjacent, right? Do you agree with that? Okay. Now with this, since the adjacent side has a length of 1, the adjacent side has a length of 1, for this drawing only, not in general, but just for this drawing, we're going to say that tan theta equals opposite, just for this drawing, because adjacent equals 1. Because we have opposite over 1. Is it okay if I just write opposite over 1? Does that make you feel better? Okay, opposite over 1 for just this drawing. So that means that the height of this triangle is tan. The height is the opposite side. Therefore, the height is tan. Okay? Equals height. Height equals tan equals opposite over 1. Are we comfortable with that? Okay. So now we're going to write, for this one, 1/2 times base times tan. Everything is positive because we're working in the first quadrant. We could do the same proof, not in the first quadrant. We'd have to mess with negatives. I don't feel like doing that. Okay, we are officially moving from the geometric picture into algebra. Well, into trig, really. Okay, I'm going to clean this up a little bit. Are you guys ready to clean it up? So I'm just going to call this sine theta over 2. Are we comfortable with that? I'm going to call this theta over 2. I'm going to call that tan theta over 2. What happens if we take the entire inequality and multiply it by 2? Gets rid of all those denominators. So we got sine theta tan. Okay? I'm going to go ahead and take the tan and write it in terms of sine and cos. That's a pretty typical thing that we do when we're working with trig stuff, is get them all in terms of sine and cos because it's easier to compare things. So I'm going to write sine. Now the reason it's helpful in this case is because we're talking about doing the squeeze theorem specifically to solve a limit that has to do with sine. So we want to deal with stuff that has to do with sine. That's why we're doing this, okay? Now, my overall goal is to get something close to sine theta over theta. That's my goal, right? I want to get a sine theta over theta, and I'm thinking of the squeeze theorem from yesterday, right? Remember the squeeze theorem from yesterday? So my goal is to get a sine theta over theta in the middle. Okay, so what I'm going to go ahead and do next is I'm going to take all 3 pieces, I'm going to divide them by sine, because when I do that, I'm getting closer to having a sine theta over theta in the middle. Right now, I only have theta in the middle. I want to have a sine theta and a theta in the middle. Does that make sense? Okay, so I'm going to divide by sine, divide by sine, divide by sine. So let's go ahead and write that step next. Sine theta over sine theta, theta over sine theta, sine theta over cos theta, oops, divided by sine theta. So I don't get confused, I'm going to put this over 1. Are you guys okay with that? I like to have, when I divide by something, I like to be fractions over fractions. That makes me feel a little bit better. Okay, so what do I have right here now? 1, okay, 1. The middle's not going to change yet. We're going to leave that. Okay. And then what should we do over here? Yeah, we're going to flip this up and kind of multiply by it. Okay. And then what happens? Okay, we just get 1 over cos. Okay. Now, we are pretty stinking close to our goal, right? The middle is just the inverted version of what we wanted. Okay. So let's think of this in terms of numbers. If I had a 1 on this side, half here, and then let's say like a 5 over here, if I was to take the 1/2 in the middle and flip it, what would that do to my symbols? It would switch them. Does that make sense? Because if I take a 1/2 and flip it, is 1 going to be smaller anymore? Well, that wouldn't be a 1/2. Let's say I had a 3/2. If I had a 3/2, I had 1 is smaller than 3/2, and I flipped the 3/2. Would 1 be smaller anymore? No, it'd be bigger now. Okay, so anytime you do something like that with a fraction, anytime you flip the fraction, say the top was smaller than the bottom was bigger, and then you flip it, you're going to have to take your inequality symbols, you're going to have to flip those too. It's the same idea as dividing by a negative. Does that make sense? Okay, so we can go ahead and we can take all of these and we can invert them, but we have to change our inequality symbols. We have to change the direction. So I'm going to say 1 is greater than or equal to sine theta over theta, greater than or equal to cos theta over 1. Miss Rice, this seems like a lot. Am I ever going to have to do this? No, I just want to show you where it came from. Okay, this was our goal, right? So we officially have the squeeze theorem, okay? So now we can go ahead and do it. So the limit as theta goes to 0 of 1 is what? Is there a place to plug in 0 for theta? No, so what's the limit? 1. Okay, the limit as theta goes to 0 of cos theta is 1. And so what is our conclusion? The limit as theta goes to 0 of sine theta over theta is 1. That's our conclusion. Okay. Now, go up just one step. What if we had done the squeeze right here? Limit as theta goes to 0 of 1 is 1. What about the limit as theta goes to 0 of 1 over cos? Well, it's cos of 0. It's still 1. So what is the limit as theta goes to 0 of theta over sine theta? It's still 1. So it doesn't matter which version you have, no matter what, it's 1. Okay, we're going to write this at the top of our page. This equals 1, and the limit as theta goes to 0 of theta over sine theta is 1. This is a big idea. So this is like highlight it. This is going to go on your cheat sheet. This proof does not need to go on your cheat sheet. The proof doesn't need to go on your cheat sheet, but this idea is huge. Okay? This idea is very important. It's a big deal. And the fact that they are interchangeable. You're going to need to know that they're interchangeable like that. That you can have sine theta over theta or theta over sine theta. It doesn't matter. They both work. Okay? All right, flip the page over. We're gonna learn the cos version, okay? So the cos version of the important one that we need to memorize is limit as x goes to 0 of 1 minus cos x over x. So what does this equal? That's what we want to figure out. We are not going to draw a proof for this one. We're just going to do this one algebraically. Same thing, what happens if you plug in 0? What if you do direct substitution? You get 0 on the bottom, and what do you get on the top? You get 1 minus 1, 0. You get 0 over 0, okay? So right now, we don't have any way we can work with it. Later, we're going to learn something where there's another way we could do it, but for today, we have to use squeeze theorem. It's another one where we're going to be able to shortcut it. All right, so here's how you do this problem. You're going to multiply. I love when things automatically go to sleep. You're going to multiply by the conjugate. Does anyone know what the conjugate would be for this problem? 1 plus cos x. We are going to FOIL the top. We are not going to FOIL the bottom. Okay? So when we FOIL the top, what do we get? You're close. 1 minus cos squared. Now, this is where we have to reach back to the summer assignment, to the trig stuff, and remember our Pythagorean identities. 1 minus cos squared is the same as sine squared. Very good. So the limit as x goes to infinity, or as x goes to 0, sorry, is sine squared. So what we're actually going to do is we are going to use the idea from the previous side of the page. Okay, and here's how we do it. This is not the simplest problem you will ever find, okay? But you're going to see how we can use that previous idea, okay? So here's what we do. Sine squared x means sine x times sine x, okay? So I'm going to take the sine x's on top and I'm going to split them. Now, I know that if I just found the limit of this, just that piece, that limit is 1. You guys agree with that? That limit is 1. What does this sine x need to find a limit of 1? What do I need on the bottom for this sine x to be good? I need an x on the bottom. Now, I just can't stick an x on the bottom. What do I have to do to get another x on the bottom? How do I get an x on the bottom of a fraction without messing up the problem? I have to put an x over x. I have to put one on the top and the bottom, okay? So, and this is going to be, we're going to do this stuff a lot in these types of problems. Whatever I want in the problem, I'm going to do it to the top and I'm going to do it to the bottom, okay? So this limit, the limit as x goes to 0 of this part is a 1. So I basically just got rid of that because now it's not messing with the problem anymore. It's there, but the limit is 1, so it's not hurting me anymore.
Oh, that's
from what we just learned on the previous side of the page. Okay, now we introduce this x over x because the one on the bottom is now helping us with this sign. So now this sign is no longer hurting us. This sine x over x is now good. So now all we have to worry about is the x over the 1 plus cos x. Okay? If I put a 0 in on top, what do I get? 0. Okay, so that's okay as long as I don't get a 0 on the bottom. Now, if I put a 0 on the bottom, what do I get? I get 1 plus 1 is 2. I get 0 over 2. Is 0 over 2 a problem? It's not a problem. So I'm going to say, okay, I'm good. I got 1 times 1 times 0 over 2. 1 times 1 times 0 over 2, which equals what? 0. And so this result is 0. So as long as I'm not getting 0 over 0, we are fine. So this answer is 0. I know. I know. I need to look it up. I'm pretty sure this one's interchangeable, but I could be wrong. I need to look that one up to see. So today's assignment is going to have a couple of the problems where you really do have to use the squeeze theorem, like on the notes last night, you actually have to do that. But more common is the ones like these, where you kind of manipulate the problem to do what you want. Okay? All right, let me get you the worksheet and we'll get started.